something is wrong with where we are. Not wrong in the way that a map is wrong when you have taken a wrong turn. Wrong in the way that the universe itself is wrong, structured differently than the models say it should be, arranged in a way that violates the assumptions at the foundation of modern cosmology, hiding something about our location in the cosmos that changes everything we think we know about the measurements we make from here. For decades, cosmologists have been assuming something so basic, so foundational, that most of them never stated it explicitly. It was simply part of the backdrop, the invisible assumption that everything else was built on top of. The assumption is this: we are in an average part of the universe, a typical region, a representative sample. The patch of cosmos our telescopes survey when they look outward is, in the relevant statistical sense, the same as any other patch. Not special, not unusual, not sitting in some anomalous region whose specific properties bias every measurement we make. That assumption may be wrong. In fact, there is a growing body of evidence, careful, peer-reviewed, independently confirmed evidence, that we are sitting inside a vast underdensity, a region of the universe where, compared to the cosmic average, there is significantly less matter, fewer galaxies, lower density, a giant bubble in the cosmic foam, and we are somewhere near the center of it. This region has a name. Astronomers call it the KBC void, after the three researchers who characterized it most precisely in 2013, Ryan Keenan, Amy Barger, and Lennox Cowie. The KBC void is approximately 2 billion light-years across. It is by a significant margin the largest underdensity ever identified in the observable universe. And we are inside it. Here is why that matters. The Hubble tension, the maddening 5 sigma discrepancy between two independent measurements of the universe's expansion rate, has been one of the most pressing unsolved problems in cosmology for the better part of a decade. Two methods of measuring how fast the universe is expanding give answers that disagree by 8%. One method looks at the early universe through the cosmic microwave background and says the expansion rate is 67.4 kilometers per second per megaparsec. The other method measures the distances to nearby galaxies using Cepheid variables and supernova and says the rate is 73 kilometers per second per megaparsec. The gap has been confirmed, refined, and hardened by increasingly precise observations, including those from the James Webb Space Telescope, and it refuses to close. But what if the two measurements are not actually measuring different things? Or what if the local measurement is being biased by where we are? What if we are inside a void, a region where the matter density is lower than the cosmic average, and that lower density causes the local expansion of space to be faster than the global average? What if we are looking outward from the bottom of a gravitational well? Or rather, from the interior of a gravitational trough, and the view from inside gives us a systematically inflated measurement of the expansion rate? This is not a fringe hypothesis. It is published in major peer-reviewed journals. It is the subject of active research programs at major universities. It has specific quantitative predictions that can be tested against observations. And as those tests accumulate, the evidence that we are in an unusual cosmic location, an unusually underdense region whose properties are distorting our most important cosmological measurements, is becoming harder to dismiss. This video is about that evidence, about the KBC void, what it is, how it was found, and what it means. about the Hubble tension and how living inside a void might explain it, about what it means for our understanding of the universe if the ground we are standing on, cosmologically speaking, is not the average ground we assumed, and about the deeper question that all of this raises, whether the cosmological principle, the bedrock assumption that the universe is the same everywhere on large scales, is actually true, or whether we have been doing cosmology from a biased location all along. Let us begin at the beginning, with the structure of the universe itself, and why voids exist in the first place. Chapter 1. The universe has a structure, and it is not smooth. If you could step outside the universe and look at it from above, if you could compress the 93 billion light-year observable sphere into something you could hold and examine, you would not see a smooth, uniform fog of galaxies. You would see a web. The cosmic web is one of the most striking features of the observable universe at the largest scales. It is a network of vast filaments, threads of matter, each one hundreds of millions of light years long and tens of millions of light years across, connecting dense nodes where galaxy clusters concentrate, surrounding enormous empty regions called voids. The filaments glow with the light of galaxies. The nodes are the brightest concentrations, where hundreds or thousands of galaxies are packed into regions millions of light years across. The voids between them are nearly empty. Regions where galaxies are rare and the average density of matter is far below the cosmic mean. This structure is not a coincidence. It is the direct consequence of the physics of the early universe. In the first fractions of a second after the Big Bang, quantum fluctuations produced tiny variations in the density of the primordial plasma. Regions that were slightly denser than average had slightly stronger gravitational pull. They attracted matter from their surroundings. Over billions of years, gravity amplified these initial fluctuations, pulling matter out of underdense regions and concentrating it into the filaments and nodes of the cosmic web. The underdense regions grew emptier as their matter was siphoned away. The dense regions grew denser. The initial tiny fluctuations, 1 part in 100,000, grew through gravitational amplification into the vast, structured cosmic web we observe today. The process is called gravitational collapse, and it is the primary mechanism by which the universe's large-scale structure formed. It is captured with impressive fidelity in the lambda CDM cosmological model and in the enormous numerical simulations. Illustris TNG, the Millennium Simulation, Eagle, the Bolshoi Simulation, that implement that model on supercomputers and generate synthetic universes that can be compared to the real one. The simulated cosmic web and the observed cosmic web look strikingly similar. The statistics of filament lengths, void sizes, cluster masses, all of it matches, at least broadly, the predictions of the standard model. Within this framework, voids are expected and predicted. They are not anomalies. Every version of the cosmic web contains voids, regions where the initial density was slightly below average, whose matter has been gradually evacuated by gravity, leaving behind expanding bubbles of relative emptiness. Voids are, in fact, the dominant volume component of the universe. More than 3/4 of the observable universe's volume is in voids of various sizes. The galaxies and clusters and filaments that appear so prominent in deep field images occupy a relatively small fraction of the total volume. What makes the KBC void unusual is not that it exists. It is its size. The voids in the standard cosmic web simulations have a characteristic scale, a typical diameter determined by the physics of structure formation, specifically by the scale at which the initial density fluctuations in the cosmic plasma were most pronounced. The most common voids in the cosmic web have diameters of roughly 30 to 300 megaparsecs. That is, roughly 100 million to 1 billion light years. Larger voids exist, but they are rarer, and there is a theoretical upper limit, loosely connected to the scale of homogeneity we discussed in previous contexts, beyond which coherent underdensities should not persist in a standard lambda CDM universe. The KBC void, as measured by Keenan, Barger, and Cowie in their 2013 paper, has a diameter of approximately 600 megaparsecs, roughly 2 billion light-years. That is at the large end of what the standard model comfortably predicts. Some analyses push the size estimate higher, to 700 or even 800 megaparsecs, depending on the tracer population used to define the void boundary and the depth of the redshift surveys being analyzed. More striking than the size alone is the depth, the magnitude of the underdensity. The interior of the KBC void has, on average, a matter density roughly 20% below the cosmic mean. In some analyses, using galaxy number counts as a proxy for matter density, the central underdensity is estimated at closer to 30%. A region 2 billion light-years across that is 20 to 30% emptier than the average universe is not a minor statistical fluctuation. It is a significant departure from the expected large-scale homogeneity, and we are inside it. The Milky Way, along with the local group of galaxies, Andromeda, the Triangulum Galaxy, dozens of satellite dwarfs, is located near the center of the KBC void. Not exactly at the center, but close enough that our line of sight in every direction encounters the low-density interior of the void before reaching the denser cosmic web beyond its boundaries. When we look out at the universe and measure its properties, when we use the distances to nearby galaxies to calibrate the cosmic distance ladder, when we observe the recession velocities of galaxies to measure the Hubble constant, when we map the distribution of galaxies and clusters across the sky, we are doing all of that from inside a cosmic hole. This is not something that was apparent from casual observation. The void is too large to see in its entirety from our position within it. No single telescope observation, no individual galaxy survey reveals the full extent of the underdensity. It took careful, systematic comparison of galaxy number counts across multiple redshift surveys and a specific theoretical framework for what the counts should look like if we were in a typical versus an atypical cosmic environment to identify and characterize the KBC void. And even after the 2013 paper, its significance for cosmological measurements remained debated, acknowledged but not fully reckoned with by the broader community. It is now being fully reckoned with. And what that reckoning reveals is that the location of our measurements may be at least partly responsible for one of the most stubborn anomalies in modern cosmology. Chapter 2: How the KBC Void Was Found. In 2013, Ryan Keenan was a graduate student at the University of Hawaii. His advisor was Amy Barger, a professor of astronomy who had spent her career studying the large-scale structure of the universe through deep galaxy surveys. The problem they were working on was a specific but apparently mundane one: measuring the number density of galaxies in a large volume around us and comparing it to the cosmic average. The tool they used was a compilation of photometric galaxy catalogs, surveys that measured the positions and approximate distances of galaxies using photometric redshifts rather than spectroscopic ones. Photometric redshifts estimate a galaxy's distance from its colors across multiple wavelength bands, without the need for detailed spectroscopic measurements of individual spectral lines. They are less precise than spectroscopic redshifts, but they can be applied to much larger samples of galaxies much more quickly, making them ideal for measuring the statistical properties of the galaxy population across large volumes. Keenan, Barger, and Cowie, the KBC, compiled galaxy counts from multiple photometric surveys covering the sky out to a redshift of approximately Z equals 0.2, corresponding to a distance of roughly 2 billion light-years or 600 megaparsecs. They measured in each redshift shell how many galaxies were detected per unit volume per unit magnitude interval. They then compared this measured number density to the expected number density based on deeper surveys of the universe at larger distances, surveys that probed the more distant universe, where, if there were a local underdensity, its effects would no longer dominate the statistics. The result was striking. At small distances, within the nearest few hundred megaparsecs, the galaxy number density was consistently below the value measured at larger distances. The local universe, out to about 300 megaparsecs in every direction, appeared to contain significantly fewer galaxies per unit volume than the more distant universe. The deficit was not marginal. In the central region of the underdensity, within roughly 100 megaparsecs, the galaxy count was roughly 50% of the value at larger distances. At the outer boundary, around 300 megaparsecs, the counts came back up toward the cosmic average. Keenan, Barger, and Cowie interpreted this as evidence for a large local underdensity, a region in which the density of galaxies, and by inference the density of matter, was systematically below the cosmic average within a sphere approximately 600 megaparsecs in diameter. They called it the local underdensity and provided the first careful characterization of its properties. The scientific community at large, gradually and somewhat reluctantly, began calling it the KBC void after its discoverers. The 2013 paper was not the first suggestion of a local underdensity. The idea that we might be in a relatively empty region of the universe had been floated in various forms for decades. In the 1990s, several researchers had noted that the distribution of galaxies in the local universe seemed somewhat sparse compared to expectations from deeper surveys. The local galaxy density, measured by the early CFA redshift survey and other catalogs, appeared lower than expected. But those early observations were interpreted as statistical noise, or as the consequence of the specific surveys used, and the hypothesis of a genuine large-scale local underdensity was not taken seriously by the majority of the community. The KBC paper was different in its scale and its rigor. By systematically combining multiple surveys, applying careful corrections for selection effects and survey completeness, and measuring the underdensity profile across a well-defined range of redshifts, Keenan, Barger, and Cowie provided a quantitative characterization that was difficult to dismiss as a survey artifact. Still, the paper's reception was mixed. Some cosmologists accepted the finding at face value and began thinking about its implications. Others argued that the photometric redshift errors in the survey compilation introduced systematic biases that could mimic an apparent underdensity. Others noted that the scale of the void, 600 megaparsecs in diameter, was at the upper end of what the standard model predicts should be possible, and suggested that it might be an unlikely but not impossible statistical fluctuation within lambda CDM rather than a genuine challenge to the model. The conversation about the KBC void might have remained at this level, an interesting but contested observational claim with uncertain implications, if it had not intersected a few years later with the Hubble tension. Chapter 3: The Hubble tension and the void connection. The Hubble tension emerged as a major cosmological problem around 2019 when the SH0ES team published a distance ladder measurement of the Hubble constant, precise enough that the disagreement with the CMB inferred value could no longer be attributed to measurement uncertainty. The 5 sigma discrepancy was real. It demanded an explanation. The theoretical community responded with a proliferation of proposed explanations: new dark energy models, extra light species in the early universe, modified gravity, each of which could, in principle, reconcile the two measurements. We have discussed these proposals in other contexts. What became relevant here was a specific and different class of explanation that did not require any new physics at all. What if the explanation was not in the physics of the universe, but in the location of the measurements? The proposal that the Hubble tension could be resolved by a local underdensity was made in its most specific and quantitative form by a group of researchers including the cosmologist Hezeve, but most prominently developed by Lucas Lombrisser at the University of Geneva, in work published in 2019 and 2020, and independently and in more detail by the team of Indranil Banik, Moritz Haselbauer, and Pavel Krupa at the University of Bonn, whose work specifically invoked the KBC void as the mechanism. The physical argument is the following. Inside a large underdensity, a region where the matter density is below the cosmic average, the expansion of space proceeds differently than in the surrounding denser regions. Gravity is the force that resists expansion. Less matter means less gravitational pull, means less resistance to expansion. A region with lower than average matter density expands faster than the cosmic average. This effect, the local enhancement of the expansion rate due to being in an underdense region, is not new physics. It is straightforward, standard general relativity. In a void, the local expansion rate H local is higher than the global expansion rate H_global. The relationship depends on the depth and the scale of the void, but for an underdensity of the magnitude and size estimated for the KBC void, the expected enhancement is on the order of a few percent. The local H_0 as measured by the distance ladder, which samples the expansion of the universe out to distances comparable to the KBC void's radius, would be systematically higher than the global H0 as inferred from the CMB, which probes the expansion history of the entire universe. The numbers are specific and can be checked. The KBC void has an estimated central underdensity of 20 to 30% below the cosmic mean. The enhancement in local expansion rate expected from such an underdensity is roughly 1 to 5%, depending on the exact void profile and the theoretical framework used. The Hubble tension requires a discrepancy of approximately 8% between the local and global values. The KBC void, on its own, does not fully account for the observed tension. It can account for part of it, perhaps half of it, but not all. This is both promising and frustrating. Promising because it demonstrates that the KBC void is a real physical effect that produces a real bias in local measurements of the Hubble constant, pointing in exactly the direction needed to explain the tension. Frustrating because it falls short of a full explanation, requiring either a deeper void than current measurements suggest, or a combination of the void effect with some additional new physics. Hasselbauer, Banach, and Krupa pursued this question in a detailed 2020 paper that compared the expected void-induced Hubble tension against the observational constraints on the KBC void's properties. Their analysis using a specific modified Newtonian dynamics (MOND) framework for the gravitational dynamics found that the KBC void of the observed size and depth could produce a local Hubble constant enhancement consistent with the measured tension. However, their conclusion depended on the specific gravitational framework they used. In standard lambda CDM gravity, the same void properties produce a smaller enhancement than in MOND, insufficient to fully close the gap. This introduced a complexity that the field has been grappling with since. The KBC void may be able to explain the Hubble tension, but whether it can depends on which gravitational framework you use. In standard lambda CDM, it can explain part but not all of the tension. In alternative gravity frameworks that predict stronger void dynamics, it can potentially explain all of it. The problem is compounded by another issue. The KBC void may itself be in tension with standard lambda CDM cosmology. Chapter 4, the void that should not exist here, is where the cosmic whole story becomes genuinely unsettling. The KBC void is large, it is deep, and according to the statistics of the standard cosmological model, it may be too large and too deep to have arisen naturally in a lambda CDM universe. The question of whether a specific large-scale structure is compatible with a given cosmological model is answered by comparing the observed structure to the statistical distribution of similar structures in numerical simulations of that model. In a lambda CDM simulation, you run a large synthetic universe, identify all the voids of a given size and depth, measure their statistical distribution, and then ask, what fraction of simulated universes contain a void at least as large and as deep as the KBC void? If that fraction is large, if KBC-like voids are common in the simulations, then the observed void is easily accommodated within the standard model. If the fraction is small, if KBC-like voids are rare in the simulations, then the observed void represents a challenge to the standard model. The analysis was performed by Hasselbauer, Banach, and Krupa in their 2020 paper using a set of large cosmological simulations, including the MXXL simulation and others. Their result? The probability of finding a void as large and as deep as the KBC void in a lambda CDM universe is extremely small. Depending on the specific simulation set and the specific definition of the void used, the quoted probability ranges from approximately 0.1% to considerably less than 0.01%. In statistical terms, the KBC void is a several sigma anomaly within lambda CDM. Not an impossible object. The simulations do occasionally produce very large voids, just very rarely. But an improbable one whose existence, if it is real, constitutes a challenge to the Standard Model's predictions for the distribution of large-scale underdensities. This creates a striking, logical situation. The KBC void potentially explains the Hubble tension, a Tushaus problem that itself constitutes a challenge to the Standard Model. But the KBC void is itself a challenge to the Standard Model. The proposed solution to one anomaly is itself another anomaly, both of them pointing in the same direction, toward a universe that is more structured, more inhomogeneous on large scales than lambda CDM predicts. This is either very bad news for lambda CDM, or it is very good news for the consistency of whatever model comes after it. If a single modification to the Standard Model, whether it is a change to dark matter's properties, a modification of gravity, or a change to the inflationary parameters that set the initial conditions of structure formation, can simultaneously explain why such large voids exist and why the Hubble constant is higher locally than globally, then the KBC void and the Hubble tension are not two separate problems. They are two symptoms of the same underlying departure from the Standard Model. That is a much more compelling scientific story than two independent anomalies requiring two independent solutions. The cosmological debate about the reality and significance of the KBC void has intensified in recent years, driven partly by new observational data. The Dark Energy Survey, which mapped the large-scale structure of the southern sky in optical and near-infrared wavelengths, provided new constraints on the local galaxy density profile that are broadly consistent with the KBC's original findings. The Extended Baryon Oscillation Spectroscopic Survey, EBOSS, added spectroscopic redshift data for millions of galaxies, improving the statistical characterization of the local underdensity. The 2-mass photometric redshift catalog, which provides photometric redshifts for 2 million galaxies across the full sky using the near-infrared 2-micron. All-Sky Survey, as its photometric base, shows a systematic deficit of galaxies in the local volume consistent with the KBC measurement. Not everyone agrees. There are published analyses that question the KBC void's significance. A 2021 paper by Kenworthy, Skolnick, and Rees, the last author being Adam Rees, the lead scientist of the SH0ES team and a Nobel laureate, argued that a careful analysis of the Type 1a supernova distribution in the local universe finds no evidence for an underdensity of the magnitude claimed by KBC. Their conclusion was that the supernova data, which measures distances with better precision than photometric galaxy counts, does not support the existence of a local void deep enough to explain a significant fraction of the Hubble tension. The counter-argument, made by Hasselbauer, Banach, and colleagues in a subsequent paper, is that the Kenworthy et al. Analysis was conducted at smaller scales, closer than the full extent of the KBC void, and therefore missed the underdensity's larger scale signature. The supernova sample used was not deep enough to probe the full 600 megaparsec extent of the void, making the Kenworthy et al. Result inconclusive rather than contradictory. This is a live scientific dispute, not a resolved one. and the resolution depends, in large part, on obtaining more and better data on the galaxy distribution and the supernova distance calibrations at distances between a few hundred and 2 billion light-years. Exactly the range in which the KBC void's properties are most diagnostic. This is a point at which James Webb becomes relevant. Chapter 5. What Webb is adding to the void story. The James Webb Space Telescope was not designed with the KBC void specifically in mind. Its primary scientific goals, observing the first galaxies, characterizing exoplanet atmospheres, studying stellar formation and evolution, are not directly about the large-scale structure of the local universe. But Webb's capabilities are relevant to the KBC void in several indirect but important ways. The first involves the distance ladder. As we have discussed extensively in other contexts, JWST's infrared precision has been used by the SH0ES team to validate and sharpen the Cepheid-based distance measurements that are the foundation of the local Hubble constant measurement. That validation confirmed the local H0 value of 73 and ruled out the systematic errors in the Cepheid calibrations that were proposed as potential explanations for the Hubble tension. By sharpening the tension, Webb has made the need for a physical explanation more urgent, and the KBC void is one of the most physically motivated explanations available. The second involves the galaxy population in the transition region. The KBC void's boundary, the wall of higher than average density that marks the edge of the underdensity and the return to the cosmic mean, lies at distances of roughly 200 to 300 megaparsecs. This corresponds to redshifts between Z equals 0.05 and Zu equals 0.1, the nearby universe, but not the extremely local neighborhood. Webb's deep field observations, while primarily designed to probe the very early universe at high redshift, are also capturing galaxies at these intermediate distances. The statistical analysis of galaxy number densities in the Webb deep fields at Z equals 0.05 to 0.1 is providing new data points on the galaxy distribution in and around the void boundary region. More specifically, the Webb-based measurements of galaxy clustering statistics at low and intermediate redshifts, measurements of how strongly galaxies cluster together on scales of tens to hundreds of megaparsecs, are sensitive to the matter density of the environment. A void produces a specific signature in the clustering statistics. Galaxies near the void interior are less clustered, with lower clustering amplitude on large scales, while galaxies in the void wall and beyond show enhanced clustering as matter has piled up at the overdense boundary. Webb's precision measurements of galaxy clustering at these scales are providing data that constrains the void's properties independently of the galaxy number count approach used by the original KBC analysis. The third contribution is more speculative, but potentially the most important. Webb's ability to characterize the Type 1a supernova population at intermediate redshifts, precisely the range relevant to the KBC void, with better precision than Hubble due to its infrared sensitivity and reduced dust correction uncertainties, will eventually allow a definitive test of whether the local supernova Hubble diagram shows the systematic offset expected from a void environment. The ongoing debate between the KBC team and the Kenworthy et al. Analysis will be resolved, in large part, by better supernova distance measurements in the Z equals 0.05 to 0.15 range. Webb is the instrument best positioned to provide those measurements. But there is a broader scientific context for the KBC void that goes beyond the Hubble tension and that connects the local underdensity to the wider pattern of anomalies in the large-scale structure data that we have discussed in various ways across multiple videos in this series. The KBC void is not the only large-scale structure anomaly in the local universe. It is part of a cluster of related findings that are beginning to build a consistent, if unsettling, picture. Chapter 6: The geometry of where we are pulled back, far enough that the entire local group, the Milky Way, Andromeda, the Triangulum Galaxy, and their dozens of satellites, is a single point. Far enough that the KBC void itself is just a bubble in the larger cosmic web. Now look at where that bubble is. The KBC void sits within a specific region of the cosmic web that has its own larger scale structure. On the void's southern boundary lies the Centaurus wall, a concentration of galaxy clusters, including the Centaurus cluster and the Hydra cluster, which represents one of the densest nearby concentrations of matter. On its northern boundary, in the direction of the Coma supercluster, another overdense structure marks the void's edge. The Great Attractor, a gravitational concentration toward which the Milky Way, Andromeda, and hundreds of nearby galaxies are being pulled, lies in the direction of the Centaurus wall at the void's boundary. The structure does not stop there. The Centaurus wall is itself part of a larger structure called the Laniakea supercluster, a vast gravitational basin identified by the cosmographer Brent Tully and colleagues in 2014, which encompasses approximately 100,000 galaxies and extends for about 500 megaparsecs across. The Milky Way sits near the edge of Laniakea's sphere of influence, in a peripheral position within the larger structure. The entire Laniakea supercluster is, in turn, embedded within the even larger network of filaments and voids that constitutes the cosmic web at its largest observable scales. At each level of this hierarchy, from the KBC void at 2 billion light-years to Laniakea at 1.5 billion, to the Great Attractor concentration within Laniakea, to our specific position within the local group on the outskirts of the Virgo supercluster, we occupy a specific geometric position within the cosmic web. That position is not average, it is not typical, it is the specific accident of initial conditions location that our particular patch of the universe happened to land in as the gravitational dynamics of structure formation played out over the past 13.8 billion years. The question that the KBC void forces us to ask is, how much does that specific geometric position affect what we observe? For most cosmological measurements, the answer was assumed to be not much. The cosmological principle, the assumption of large-scale homogeneity, was invoked as the reason this answer should be approximately correct. On the scales relevant to cosmological measurements, the universe averages out. The specific local environment should not matter. The global average should dominate. The KBC void challenges that assumption at a specific, measurable level. 2 billion light-years is large. 20 to 30% underdensity is deep. And the specific effect it produces, an enhancement of the local expansion rate, targets precisely the measurement that exhibits the most significant anomaly in modern cosmology. The Hubble tension is not a random discrepancy between two unrelated measurements. It is a discrepancy between a measurement that samples the local universe, the distance ladder, and a measurement that infers the global average, the CMB. The KBC void, sitting between the local and the global, is exactly the kind of structure that could produce exactly this kind of discrepancy. There is another anomaly in the local universe that the KBC void may be connected to, and it is one that has received less attention but is equally puzzling. It is the observation that nearby galaxy clusters, the most massive gravitationally bound structures in the local universe, appear to be moving in a coordinated way across the sky, in a direction that is not explained by the gravitational effects of the known large-scale structures. This coherent motion has been called the dark flow by some researchers, and while its reality and magnitude are debated, the direction of the motion, toward the concentration of mass at the void's boundary, is consistent with what would be expected from the gravitational dynamics of the KBC void environment. The void itself is not static, it is expanding. The interior of the KBC void is emptying out over time as gravity pulls its remaining matter toward the overdense boundaries, the walls and filaments of the surrounding cosmic web. The galaxies inside the void are being displaced, pushed outward by the pressure gradient between the underdense interior and the denser boundary, in a process sometimes described by the memorable phrase cosmic evacuation. The Milky Way, sitting near the center of this evacuating region, is itself being pushed outward in the direction of the void wall. This outward motion is superimposed on the cosmological expansion. When we measure the recession velocity of a distant galaxy and interpret it as a measurement of the Hubble constant, we are measuring the sum of the cosmological expansion and the peculiar velocity, the motion of the galaxy relative to the Hubble flow, driven by the gravitational dynamics of the local environment. In a void, the peculiar velocities of galaxies near the void interior are systematically directed outward, away from the void center. The Milky Way has a specific peculiar velocity, a motion relative to the cosmic rest frame, that reflects its position within the KBC void environment. This peculiar velocity has been measured. The local group is moving at approximately 630 kilometers per second, relative to the cosmic microwave background rest frame, a motion that encodes information about all the gravitational influences within a few hundred megaparsecs. Decomposing this motion into its contributing factors, the Great Attractor Pull, the Shapley Supercluster Pull, the Void Repulsion, is an ongoing research program that is directly relevant to the KBC void story. The repulsive contribution from the void's underdensity, the gravitational push away from the void center, should be a measurable fraction of the total peculiar velocity. And comparing that contribution to the measured value provides an independent constraint on the void's depth and mass profile. The Shapley supercluster deserves specific mention here because it represents the single largest concentration of mass in the nearby universe, and its gravitational influence extends across the same scales that the KBC void occupies. The Shapley supercluster is approximately 650 million light-years away, at the far boundary of the KBC void, and contains dozens of galaxy clusters and tens of thousands of galaxies, with a total mass comparable to several times 10 to the 16th solar masses. It pulls on the local group at the same time as the void's underdensity pushes. The net peculiar velocity of the local group reflects the sum of these competing gravitational influences, and disentangling them requires a detailed gravitational reconstruction of the full mass distribution within a sphere of approximately 1 billion light-years centered on us. That reconstruction has been attempted multiple times, most recently using the 2 mass ++ peculiar velocity survey, which measures the peculiar velocities of thousands of galaxies across the local universe using their infrared luminosities as distance indicators. The reconstructions consistently find that both the Great Attractor Complex and the Shapley supercluster contribute substantially to the local group's motion, and that the contribution from the void repulsion, while present and consistent with the KBC void's estimated depth, is entangled with those of the surrounding overdensities in ways that require careful modeling to separate. Early analyses suggest the contribution from the KBC void to the local group's peculiar velocity is consistent with the void's estimated properties. This is not a definitive confirmation. The decomposition of the peculiar velocity into contributing factors is uncertain, and the relative contributions of different structures are debated. But the consistency is another piece of evidence pointing in the same direction. We are in an underdense region, and that region is dynamically affecting our position and motion in the cosmos in ways that are beginning to be measurable. Chapter 7: The Cosmological Principle. Under siege. The cosmological principle is the load-bearing wall of modern cosmology. It is the assumption that, on sufficiently large scales, the universe looks the same from any location and in any direction. Homogeneous, the same everywhere. Isotropic, the same in every direction. Without this assumption, the Friedmann equations, the mathematical description of the universe's expansion derived from general relativity under the cosmological principle assumption, do not apply. And without the Friedmann equations, the standard framework for interpreting cosmological observations falls apart. The cosmological principle was introduced by Einstein in 1917, not because he had empirical evidence for it, but because the mathematics of general relativity applied to an inhomogeneous universe was intractably complex. The cosmological principle was a simplifying assumption that made the equations solvable. It was justified post hoc by the observed large-scale smoothness of the cosmic microwave background. The fact that the CMB temperature is the same to within 1 part in 100,000 in every direction. As evidence that the universe was indeed approximately homogeneous at early times. But the CMB homogeneity applies to the universe at the time of recombination, 380,000 years after the Big Bang. Since then, gravity has had 13.8 billion years to build the cosmic web, the filaments, clusters, and voids of the large-scale structure. The question is not whether the universe was homogeneous at recombination. It clearly was to high precision. The question is whether it is approximately homogeneous today on the scales relevant to cosmological measurements, specifically the scales of a few hundred megaparsecs to a few billion light-years that the Hubble Constant Measurements probe. The KBC void directly challenges this assumption at the relevant scale. A 2 billion light-year underdensity that is 20 to 30% below the cosmic mean is not a small perturbation. It is a large departure from homogeneity on exactly the scales that matter for the local Hubble constant measurement. If the standard framework assumes we are in a representative location, and we are demonstrably in an unusual location, then every cosmological parameter derived from local measurements, not just the Hubble constant, but potentially the matter density, the dark energy density, the spatial curvature, is subject to a systematic bias that the standard analysis does not account for. This is a profound methodological problem. The entire enterprise of precision cosmology, the multi-decade project of measuring the universe's parameters with increasing accuracy and using those measurements to test and constrain theoretical models, has been conducted under the assumption that the cosmological principle holds at the relevant scales. If that assumption is significantly violated by the actual structure of the local universe, then some fraction of the precision in precision cosmology is illusory. The measurements are precise in the sense of being reproducible and low in statistical uncertainty. They may not be accurate in the sense of correctly representing the global properties of the universe, if they are systematically biased by the non-average properties of our cosmic location. The community's response to this challenge has been careful and nuanced. On one side, researchers like Hasselbauer, Bonnick, and Krupa argue that the KBC void is real, that it is in tension with lambda CDM's predictions for the void size distribution, and that its dynamical effects are large enough to account for a significant part of the Hubble tension. On the other side, researchers associated with the SH0ES program and the broader Hubble tension literature argue that the supernova data does not support a local underdensity of the required magnitude, and that the Hubble tension must be explained by new physics rather than by the geography of our cosmic neighborhood. Both sides are in agreement on one thing: the question matters enormously. If the KBC void is as large and as deep as the KBC measurement and its successors suggest, and if the standard model's simulations genuinely show that such a void is improbable in a lambda CDM universe, then the KBC void is not just a potential explanation for the Hubble tension. It is itself a problem for the standard model, requiring its own explanation. And the explanations that have been proposed for why the KBC void exists, why there is a 2 billion light-year underdensity in our cosmic neighborhood that is improbably large given the standard model, are themselves among the more radical proposals in contemporary cosmology. They include the possibility that the initial conditions of the universe differed from the standard inflationary prediction in ways that produced more power on large scales. They include alternative gravity frameworks that predict stronger void formation and larger underdensities than general relativity in the lambda CDM context. And they include the possibility that the KBC void is simply an unlikely but not impossible statistical fluctuation, the cosmic equivalent of being dealt a very unusual hand of cards. The distinction between these possibilities matters because they have different observational signatures that future surveys can test. A void produced by enhanced large-scale power in the initial conditions leaves specific signatures in the CMB and in the galaxy power spectrum on large angular scales. A void produced by alternative gravity dynamics affects the peculiar velocity field in ways that differ from standard gravity predictions. A purely statistical fluctuation has no specific signature beyond its existence. Separating these possibilities requires more data, better characterized galaxy number, counts in the void interior and at its boundaries, better peculiar velocity measurements of the galaxies within and around the void, better maps of the matter distribution at distances of hundreds of megaparsecs. The Vera-Rubin Observatory's legacy survey of space and time, when it begins full operations, will provide the deep, wide-area galaxy catalog needed to characterize the void's properties with significantly better precision than current surveys allow. JWST, as noted, is contributing incrementally through its intermediate redshift galaxy population measurements. The cosmological principle is not yet disproven. The evidence for the KBC void, while substantial, is contested. The Hubble tension may have multiple contributing causes. The standard model may ultimately accommodate the KBC void as an unlikely but statistically permitted fluctuation. But the siege of the cosmological principle is underway, and the weapon being wielded is the specific, measurable fact of where we are. It is worth pausing here to appreciate exactly what is at stake in this debate, because it is easy to treat it as a narrow, technical disagreement between specialists and miss its broader significance. The cosmological principle is not just a mathematical convenience. It is the reason that cosmology, the science of the universe as a whole, is possible at all in its current form. Without homogeneity and isotropy at large scales, there is no single expansion rate of the universe. There is only the expansion rate at our location and the expansion rate at some other location, and these need not be the same. Without the cosmological principle, there is no unique density of matter in the universe. There is only the density here and the density there, and the enormous challenge of figuring out how to average those into something meaningful. Modern cosmology has been extraordinarily successful precisely because the cosmological principle, as an approximation, works well enough that it has allowed us to build a coherent, predictive, testable model of the universe's history and composition. The CMB power spectrum, the baryon acoustic oscillations, the history of structure formation. All of these are measured and interpreted within the cosmological principle framework, and they produce consistent, beautiful, precise results. The KBC void is not demolishing that framework. What it is doing is identifying a specific scale, approximately 2 billion light-years, at which our specific location departs significantly from the cosmic average, and pointing out that some of our most important cosmological measurements are made on exactly that scale. It is a precision challenge, not a demolition. It is asking, have we been fully accounting for the fact that our measuring tape is located in a non-average part of the ruler? That question, asked precisely, tested rigorously, and answered honestly, is exactly the kind of question that drives science forward. Whether the answer ultimately vindicates or challenges the cosmological principle, the asking of it is the right thing to do. Chapter 8: The Other Voids. We are not alone in the whole. The KBC void is the most important underdensity in the story of our cosmic location, but it is not the only void worth examining. The universe, at every scale, is structured around emptiness. The cosmic web is as much defined by what is absent as by what is present. and the survey of large voids in the observable universe, which has accelerated dramatically in the era of wide-field galaxy surveys, reveals a pattern that is both scientifically informative and philosophically striking. We are, in a very specific sense, a species that lives in a hole within a hole. Let me explain what that means. The KBC void is a large-scale underdensity approximately 2 billion light-years across. But within the KBC void, there is additional structure. The KBC void is not uniformly empty. It has an interior that contains smaller-scale structures, filaments, smaller clusters, individual galaxy groups, distributed within the larger underdense region. And some of those interior regions are themselves underdense relative to the KBC void's own average interior density. Our immediate neighborhood, the local void, is one of those. The local void is a much smaller underdensity, extending primarily in the direction of the constellation Aquila, with a diameter of roughly 150 to 200 megaparsecs, approximately 500 to 650 million light-years. It was first identified by Brent Tully and J. Richard Fisher in the 1980s using the distribution of nearby galaxies in the local group's neighborhood, and it has been characterized in increasing detail by subsequent surveys. The local void is essentially empty. The galaxy density within it is among the lowest measured anywhere in the nearby universe. Its boundary, where it meets the denser cosmic web structures beyond, forms part of the defining edge of the local group's dynamical environment. The local group sits on the boundary of the local void, not within its deepest interior. The Milky Way is being pushed away from the local void's center. Its local peculiar velocity has a component directed away from the void, consistent with the gravitational repulsion expected from the underdensity. The cosmographer Brent Tully, whose decades of work mapping the local universe has produced some of the most detailed, three-dimensional reconstructions of the nearby cosmic web, estimated in a 2008 paper that roughly 1/4 of the local group's total peculiar velocity relative to the CMB frame can be attributed to the repulsive influence of the local void. So we have a nested structure. The local group sits on the edge of the local void, which itself is embedded within the KBC void, which in turn is embedded within the larger cosmic web. At each scale, we occupy a position that is influenced by the underdense region in our immediate surroundings. The gravitational dynamics of our location are a superposition of attractions from the overdense structures: the Virgo cluster, the Great Attractor, the Shapley supercluster, and repulsions from the underdense regions, the local void, and the KBC void. This nesting of underdensities has a specific implication for the Hubble tension debate that is worth making explicit. The enhancement of the local expansion rate from being inside a void operates at every scale. The local void, smaller and closer, produces a local expansion enhancement that is relevant at the smallest scales of the Hubble constant measurement. The KBC void, larger and extending to greater distances, produces an enhancement relevant at intermediate scales. Together, they produce a cumulative effect that is spread across the full range of distances sampled by the local Hubble constant measurement. This is not a coincidence that makes the explanation more complicated. It is a natural feature of the hierarchical cosmic web. Underdensities exist at every scale, and being located inside the cosmic web rather than outside it, are inevitably influenced by multiple levels of the hierarchy simultaneously. The question is not whether the void-induced expansion enhancement is present. It is at every level. But whether its cumulative magnitude is sufficient to explain the full 8% Hubble tension, or whether some additional physical ingredient is also required. The most careful analysis of the combined effect of the local void and the KBC void on the local expansion rate suggests that together they can produce an enhancement of approximately 2 to 4% above the global average. The Hubble tension requires approximately 8%, so the voids account for roughly a quarter to half of the observed discrepancy. This is a significant fraction, too large to dismiss as irrelevant, but insufficient on its own to close the tension entirely. The remaining 4 to 6% must come from either new physics, additional underdensities beyond the KBC void, or systematic errors in one of the measurements that remain unidentified. There are other voids of note in the nearby universe that contribute to the broader picture. The Boötes void, discovered in 1981 by Robert Kirshner and colleagues in a survey of galaxies in the direction of the constellation Boötes, was one of the first truly large voids identified in the galaxy distribution. Approximately 330 megaparsecs, about a billion light-years, in diameter, the Boötes void is nearly circular and remarkably empty. It contains only a handful of known galaxies in its interior, compared to the hundreds of thousands that would be expected if the galaxy density within it matched the cosmic average. At the time of its discovery, it was the largest known void in the universe, and it caused significant discussion about whether such large underdensities were compatible with the then current models of structure formation. The Boötes void is not inside the KBC void. It is at a distance of roughly 700 megaparsecs from us, beyond the KBC void's boundary. Its existence is relevant as an example of the scale and depth of underdensities that the actual universe produces, and as one of the data points in the ongoing statistical comparison of observed voids against theoretical predictions. The Boötes void, like the KBC void, sits at the large end of the void size distribution. Improbable, but not impossible in a lambda CDM universe, depending on whose simulations you use and what you consider the relevant comparison sample. Before leaving the survey of voids, it is worth pausing on one more that has a specific distinctive quality among all the underdensities catalogued in the nearby universe. The Eridanus supervoid, identified in the direction of the constellation Eridanus, sits at a distance of roughly 700 megaparsecs from us. It is not the largest void known, nor the deepest. What makes it distinctive is its potential connection to the single most anomalous feature in the cosmic microwave background, the CMB cold spot. The cold spot is another large-scale anomaly that has been discussed in connection with void cosmology, though its nature and significance remain controversial. The CMB cold spot is a region of the cosmic microwave background, in the direction of the constellation Eridanus, that is approximately 70 microkelvin colder than the surrounding CMB average, making it the most prominent temperature anomaly in the entire CMB sky. Several explanations have been proposed for its origin, including a statistical fluctuation in the CMB itself, a topological defect from the very early universe, or a signature of the integrated Sachs-Wolf effect from a large void in the foreground. The integrated Sachs-Wolf effect is a mechanism by which CMB photons passing through a large underdensity gain or lose energy depending on whether the void is growing or shrinking as the photon traverses it. In a universe dominated by dark energy, voids grow over time. They empty out faster than gravity can halt the expansion. And photons passing through growing voids lose a small amount of energy compared to photons that pass through undisturbed space. This produces a cold spot in the CMB aligned with the foreground void. A galaxy survey in 2015 identified a large underdensity in the direction of the CMB cold spot at a redshift of approximately z equals 0.2, with a diameter of roughly 200 megaparsecs. This Eridanus void, or CMB cold spot supervoid, was initially interpreted as a potential explanation for the cold spot through the integrated Sachs-Wolf effect. Subsequent analyses found that the Eridanus supervoid, while real, is not deep enough or large enough to produce the full magnitude of the CMB cold spot through the standard integrated Sachs-Wolf mechanism. The cold spot remains partially unexplained. The significance of the cold spot for the KBC void story is not in the specific explanation of the cold spot, which remains uncertain. It is in what the cold spot illustrates about the relationship between large-scale underdensities and the CMB. The CMB, which we use as the early universe anchor for the global Hubble constant measurement, is itself influenced by the large-scale structure of the universe through which the CMB photons have passed since recombination. Voids and overdensities between us and the CMB last scattering surface imprint their signatures on the CMB temperature map through the integrated Sachs-Wolf effect and other secondary anisotropies. If the universe is more inhomogeneous than the standard model predicts, if large voids are more common and deeper than lambda CDM simulations suggest, then these imprints are systematically larger than the standard model accounts for, and the CMB-based cosmological parameter estimates carry a systematic bias. This is a subtle but important point. The Hubble tension is framed as a discrepancy between the local Hubble constant, too high in the local measurement, and the global Hubble constant, inferred from the CMB. We have been focusing on why the local measurement might be biased upward by the KBC void. But the other side of the tension, the CMB inferred value, is not necessarily the correct global value either. If large foreground voids are imprinting their signature on the CMB through the integrated Sachs-Wolf effect in a way that is not properly modeled, then the CMB inferred Hubble constant could also carry a bias in the downward direction, since voids that cool the CMB photons would mimic the effect of a slightly lower expansion rate if not properly accounted for. Both measurements might be biased in opposite directions. Together, both biases contribute to the observed tension. The observational case for widespread large-scale inhomogeneity, voids and overdensities at the scales of hundreds to thousands of megaparsecs, is not confined to the specific examples catalogued above. Statistical analyses of the CMB on large angular scales have identified several anomalies. The low quadrupole power, the alignment of the quadrupole and octupole moments, the hemispherical power asymmetry, that are difficult to explain within the standard lambda CDM framework, and that some researchers have interpreted as signatures of large-scale structure beyond the standard model's predictions. Each of these anomalies is individually debated. Each has proposed explanations within the standard framework, but collectively they form a pattern, a consistent set of observations at the largest cosmic scales that appear to favor a universe that is more inhomogeneous, more structured, more departing from the cosmological principle than the standard model predicts. The KBC void is the most specific and most directly relevant to local Hubble constant measurements, but it is part of a broader observational picture that the next generation of surveys is only beginning to assemble in full. Chapter 9: Living in a Hole. What it actually changes. Let us be concrete about what the KBC void changes and what it does not. It does not change the physics of the universe. The laws of physics, general relativity, quantum field theory, nuclear physics, are the same inside the KBC void as outside it. The expansion of the universe is happening everywhere. Dark matter and dark energy are distributed throughout the cosmos, including within the void. The Big Bang happened. The CMB is real. The large-scale structure of the cosmic web is real. None of this is challenged by the KBC void. What the KBC void changes, or more precisely, what its existence forces us to reconsider, is the interpretation of specific measurements made from our specific location. It is the difference between the universe's properties and our local window onto those properties. Let us go through the affected measurements one by one. The Hubble constant, as measured locally, is the most directly affected. The distance ladder, the chain of overlapping distance measurements from parallax to Cepheids to Type 1a supernovae, samples the expansion of the universe out to distances of a few hundred megaparsecs. All of that volume, in the KBC scenario, is inside the underdensity. The locally measured expansion rate reflects the expansion rate of the void interior, which is faster than the global average. The discrepancy between the local measurement, 73, and the CMB inferred global average, 67.4, is, in this interpretation, partly a consequence of where the local measurement was made, not purely a signal of new physics. The matter density, as inferred from local surveys of the galaxy distribution, is also affected. Galaxy surveys that measure the density of galaxies per unit volume within the KBC void radius will infer a matter density below the cosmic average. If those surveys are used to calibrate the relationship between galaxy density and total matter density, including dark matter, then the locally inferred matter density will be systematically lower than the true cosmic average. This has cascading effects on cosmological parameter estimates that use the local matter density as an input. There is a specific numerical argument worth presenting here, because it is rarely stated clearly, and it illuminates how the KBC void connects to the full suite of cosmological anomalies, rather than just the Hubble tension. The sigma 8 tension, a lesser known but equally real cosmological discrepancy in which the measured amplitude of matter, density fluctuations, on scales of 8 megaparsecs is lower in weak gravitational lensing surveys than in CMB-based predictions, may also be partially explained by our location within the KBC void. Weak gravitational lensing surveys measure the distortion of distant galaxy shapes by the matter distribution between us and them. The lensing signal is sensitive to the density fluctuations along the line of sight. If we are in an underdense region, the matter density we are probing along nearby lines of sight is systematically below the cosmic average, producing a lower observed sigma 8 than the CMB predicts for the universe as a whole. The sigma 8 tension, like the Hubble tension, fits naturally within the KBC void explanation. This is a crucial point. The KBC void hypothesis does not just address one anomaly. It potentially addresses multiple independent discrepancies simultaneously: the Hubble tension, the sigma 8 tension, and the statistical properties of the local galaxy density distribution. The fact that a single physical explanation, we are in a large local underdensity, predicts the direction and approximate magnitude of multiple independent anomalies is a strong argument in its favor. In science, an explanation that resolves several puzzles at once is far more compelling than one that addresses only the specific problem it was designed to solve. The power of this multi-anomaly connection deserves to be stated explicitly in numerical terms. Consider what the KBC void predicts for each major cosmological discrepancy. For the Hubble tension, a 20 to 30% underdensity on 300 megaparsec scales produces an expansion rate enhancement of 2 to 5% above the global average, accounting for roughly 25 to 60% of the observed 8% discrepancy. For the sigma 8 tension, where the observed matter clustering amplitude is roughly 5 to 10% below the CMB prediction, a similar underdensity produces a comparable suppression of the local matter clustering signal, directionally consistent and plausibly of the right magnitude. For the local galaxy density, the KBC measurement itself establishes the 20 to 30% deficit that is the void's defining observational signature. All three of these predictions point in the same direction, with magnitudes that are consistent, within uncertainties, with a single common cause. That alignment across three independent observables from three independent measurement techniques is the strongest statistical argument for taking the KBC void seriously as a contributor to cosmological anomalies, rather than dismissing it as a localized curiosity. This is not to say the KBC void explanation is proven. It is not. Each of the connections described above is contested by at least some researchers. The magnitude of the Hubble tension explained by the void falls short of the full tension. The sigma 8 connection is qualitatively consistent, but not yet quantitatively tested at the precision required for a definitive statement. But the pattern is there, and it points in the same direction. There is a deeper philosophical implication of living in an underdense region that goes beyond the specific measurement biases. It concerns the concept of a fair sample. In any empirical science, the validity of a measurement depends on whether the sample being measured is representative of the population being characterized. A biologist measuring the average height of a population will get a misleading answer if their sample consists entirely of professional basketball players. A geologist dating the age of the Earth from rock samples will get a misleading answer if all their samples come from a single unusual geological formation. The validity of the measurement depends on the representativeness of the sample. Cosmology has always operated under the implicit assumption that our local universe is a fair sample of the global universe, that the measurements we make from our specific location are representative of the universe's average properties. The cosmological principle formalizes this assumption. If the universe is homogeneous and isotropic on large scales, then any location is as good as any other for making cosmological measurements, and the local sample is by definition representative. The KBC void challenges this assumption at a specific, measurable level. Not at all scales and in all respects. On the very largest scales, the universe does appear to average out to near homogeneity. But at the specific scales of hundreds of megaparsecs that are most relevant to local Hubble constant measurements, at those scales, our location is demonstrably not average. We are in a region that is 20 to 30% below the cosmic mean density. And that non-averageness is precisely the scale at which our most important cosmological measurements are made. The philosopher of science would identify this as a form of observation selection effect, a systematic bias introduced by the fact that the observer is not a random sample from all possible observation locations, but a specific observer at a specific location with specific properties. We are in the KBC void not by random chance, but because the KBC void is the environment in which our galaxy formed and exists. We could not have observed the universe from a randomly selected location in the cosmic web. We can only observe it from here, from the location where we happen to be. Observation selection effects are a recognized and important source of systematic bias in many fields of science, and cosmology is not immune to them. The anthropic principle, the observation that the universe's properties, as observed from Earth, must be compatible with the existence of observers on Earth, is a specific application of observation selection logic to cosmology. The KBC void's potential bias on cosmological measurements is a more mundane but equally real application of the same logic. The measurements we make from our specific location in the cosmic web are influenced by the properties of that location, and those properties are not chosen randomly. This does not mean cosmology is impossible or that our measurements are meaningless. It means that cosmological measurements made from within the KBC void must be corrected for the void's influence before they can be compared to global theoretical predictions. This is analogous to correcting parallax measurements for the Earth's position in its orbit, or correcting supernova light curves for the recession velocity of the host galaxy. It is a systematic effect that can be modeled and removed once its magnitude is known. The magnitude is not yet known with sufficient precision to make the correction definitively. That is the current state of the field. But the direction is clear, the physical mechanism is understood, and the data needed to pin down the correction is being accumulated by the surveys underway and planned for the coming decade. Chapter 10. The Future of the Measurement. If the KBC void is real and its properties are as characterized by the best current analyses, how do we confirm it beyond remaining doubt and determine its exact contribution to the cosmological anomalies? The answer is data. Specifically, several very different types of data that can be combined to give an increasingly precise picture of the mass distribution in our cosmic neighborhood. The first and most direct approach is improved galaxy surveys. The galaxy number density is the most straightforward probe of the matter distribution. Where there are more galaxies, there is more matter. Where there are fewer, there is less. But galaxy surveys face a fundamental challenge. They measure the distribution of luminous matter, not total matter, including dark matter. the relationship between galaxy number density and total matter density, the galaxy bias, depends on the properties of the galaxies being counted and the environment they are in. And this relationship is uncertain enough that galaxy counts alone cannot definitively characterize the void's total mass profile. The best current galaxy surveys probing the KBC void scales are the two mass photometric redshift catalog, the Dark Energy Survey, and the Extended Baryon Oscillation Spectroscopic Survey. Each covers a different area of sky, uses a different selection of galaxies, and has different depth and completeness. Their combined data is consistent with the KBC void's existence and approximate properties, but the remaining uncertainties are large enough that the void's exact depth, size, and shape are not yet pinned down. The Vera Rubin Observatory's legacy. Survey of Space and Time, LSST, will transform this situation when it reaches full operations. LSST will survey the entire southern sky in 6 photometric bands to a depth significantly greater than any previous wide-area survey over 10 years. Its photometric redshift catalog will include billions of galaxies out to redshifts of Z equals 1 and beyond. Within the redshift range relevant to the KBC void, the LSST galaxy number counts will provide a measurement of the void's density profile with statistical precision orders of magnitude better than current surveys. Systematic uncertainties, photometric calibration, star-galaxy separation, atmospheric effects will be the limiting factors, and the LSST team has invested heavily in characterizing and correcting these systematics. The second approach is peculiar velocity surveys. The peculiar velocities of galaxies, their motions relative to the smooth Hubble flow, encode direct information about the gravitational potential field, and therefore about the total mass distribution, including dark matter. A galaxy near the center of the KBC void has an outward peculiar velocity driven by the void's underdensity. A galaxy on the void wall has an inward peculiar velocity being pulled toward the overdense boundary. The pattern of peculiar velocities across the void region traces the underlying mass distribution in a way that is independent of galaxy bias. Measuring peculiar velocities requires knowing both the recession velocity of a galaxy, easy, from its redshift, and its distance independently of the redshift, hard, requiring a secondary distance indicator. The most precise secondary distance indicators for peculiar velocity surveys are the Tully-Fisher relation for spiral galaxies, the relationship between a spiral galaxy's rotation speed and its intrinsic luminosity, and the fundamental plane relation for elliptical galaxies, relating a galaxy's size, surface brightness, and velocity dispersion to its intrinsic luminosity. The Cosmic Flows program, led by Brent Tully and his collaborators, has been systematically measuring galaxy distances using these relations and building the most comprehensive, peculiar velocity catalog of the local universe. The fourth data release of the Cosmic Flows program, Cosmic Flows 4, published in 2022, includes distance measurements for nearly 56,000 galaxies out to distances of approximately 600 megaparsecs. The peculiar velocity field reconstructed from this dataset is the most detailed map of the local cosmic dynamics ever assembled, and it is directly relevant to characterizing the KBC void. The void-induced outflow from the KBC void interior should be visible as a coherent pattern in the peculiar velocities of galaxies within the void boundary. and the cosmic flow's 4 data is beginning to resolve this pattern with sufficient fidelity to constrain the void's properties independently of the galaxy number counts. The third approach is weak gravitational lensing, the statistical distortion of background galaxy shapes by the mass distribution in the foreground. Weak lensing is sensitive to all mass along the line of sight, including dark matter, making it the most direct probe of the total matter density field. It does not require assumptions about galaxy bias. A void in the foreground produces a characteristic deficit in lensing signal. Background galaxies behind the void are distorted less than expected because there is less foreground mass to do the distorting. The detection of the lensing signal from large cosmic voids, including potential confirmation of the KBC void through its weak lensing signature, requires large, deep surveys of faint galaxy shapes. The Dark Energy Survey and its successor, the Legacy Survey of Space and Time, are the primary instruments for this measurement. JWST contributes at smaller scales, providing exquisitely precise shape measurements for galaxies in its deep fields that can be used to calibrate the weak lensing methodology. The fourth approach, potentially the most decisive for the Hubble tension specifically, is the extension of the Type 1a supernova Hubble diagram to higher redshifts within and beyond the KBC void. The current Hubble tension debate partly hinges on whether the local supernova Hubble diagram, the relationship between supernova distance and recession velocity at low redshifts, shows the systematic offset expected from the void environment. The Kenworthy et al. Analysis found no evidence for such an offset. The KBC team argues the Kenworthy analysis was not sensitive to the offset because it did not extend to large enough distances. The definitive test requires Type 1a supernova distances measured at redshifts between z equals 0.05 and z equals 0.15, the range that probes from the void interior to well beyond the void boundary. In this redshift range, the transition from the void's enhanced expansion rate to the ambient cosmic expansion rate should produce a subtle but detectable change in the slope of the Hubble diagram. The precision of this measurement demands Type 1a supernova distances with uncertainties below a few percent, which in turn demands precise photometry and precise spectroscopic classification of the supernova events. JWST is providing exactly this precision for supernova observed in its ongoing programs. The JWST SH0ES program has already used Webb to observe Cepheids and supernovae in nearby calibration galaxies. The broader supernova community is using Webb to extend the supernova sample to higher redshifts with better photometric accuracy than Hubble achieved. Within the next several years, the supernova Hubble diagram at the relevant redshifts will be pinned down with sufficient precision to definitively test whether the KBC void hypothesis is consistent with the data or ruled out by it. The convergence of LSST galaxy surveys, cosmic flow's peculiar velocity catalogs, weak lensing mass maps, and JWST supernova distances will, within the next decade, produce an observational answer to the question of whether the KBC void is large, enough and deep enough to explain a significant fraction of the Hubble tension. The answer may confirm the void hypothesis, it may rule it out, or it may provide a partial confirmation that requires additional new physics to complete the explanation. What it will not do is leave the question at its current level of ambiguity. It is also worth noting what happens if the KBC void is confirmed to be exactly as characterized and to account for only part of the Hubble tension. That partial explanation is itself scientifically extraordinary. It means that for decades, the most precisely measured cosmological parameter, the expansion rate of the universe, has been systematically biased by geography. By the specific, physically unremarkable fact that our galaxy formed in an underdense region, and our measurements of the local expansion have been inflated accordingly. The discovery that our most fundamental cosmological ruler carries a systematic calibration error from our position in the cosmic web would be one of the most significant methodological revelations in the history of the science. Not because it overturns anything, but because it demands that every cosmological measurement made from within the KBC void be revisited with the void correction applied. The entire parameter space of the standard model, every number in lambda CDM that was constrained using local observations, would need to be re-examined through the lens of our non-average location. That is an enormous undertaking, but it is also an enormously productive one. Correcting for the void environment would sharpen the distinction between what the local universe genuinely differs from the standard model in requiring new physics, and what is simply a measurement artifact of our position, requiring only honest bookkeeping. It would allow the cosmological community to identify, more clearly than it currently can, which anomalies are truly anomalous, and which are artifacts of the biased sample. Science is converging on the answer. And the answer, whatever it is, will change something fundamental about how we understand our place in the cosmos. There is one more dimension of the void story that deserves specific attention before we turn to the conclusion, and it concerns not the measurement of cosmological parameters, but something closer to the fundamental question of what kind of universe we live in. The existence of the KBC void, even setting aside its implications for the Hubble tension, raises a pointed question about the cosmological principle. We have noted that the KBC void is statistically unusual within lambda CDM. The probability of finding a void this large and this deep in a standard simulation is small. This could be interpreted as either A, we got unlucky and live in a rare region, or B, the standard model is wrong about the abundance of large voids, meaning the universe is more inhomogeneous than lambda CDM predicts. Option B would require a modification to the standard model at the level of either the inflationary initial conditions, the dark matter properties, or the gravitational dynamics of large-scale structure formation. Any of these modifications has cascading implications for the rest of cosmology. A modification to inflationary initial conditions changes the predictions for the CMB power spectrum. A modification to dark matter properties changes the predictions for the galaxy power spectrum and for the halo mass function. A modification to gravitational dynamics changes the predictions for the growth of structure across all cosmic epochs. The fact that these modifications might simultaneously explain the KBC void's anomalous size, the Hubble tension, and the sigma-8 tension, as several published analyses suggest, is the most compelling version of the argument that something in the standard model needs to change. The anomalies are not pointing in random directions. They are pointing consistently toward a universe that is more structured, more dynamically active in its void and overdensity formation than lambda CDM predicts. What that universe looks like, what specific modification to the physics produces the right combination of large voids, enhanced local expansion, and suppressed matter clustering, is what the theoretical community is actively working to determine. The KBC void is not just a local curiosity. It is a probe of fundamental cosmological physics, visible from inside. Conclusion. Here is the thing about living inside a cosmic hole. You would not know. There is no visible edge, no wall you could point a telescope at and say, there, that is where the void ends and the universe's average density begins. The transition from underdense interior to cosmic average is gradual, smeared across hundreds of millions of light years by the same gravitational dynamics that created the void in the first place. From inside, you cannot see out. You can only see what is here, which is the inside of the void, which looks like the universe. And that is precisely the problem. The universe, as seen from inside the KBC void, looks like the universe. The stars, the galaxies, the great web of structure, all of it is visible and measurable and apparently consistent with itself. The void does not announce itself with a blank space or a silence or a visible boundary. It reveals itself only through careful statistical comparison of the number counts of galaxies at different distances. The kind of analysis that requires decades of survey data and the specific theoretical framework to know what you're looking for. This is a profound epistemological predicament. Our entire cosmological knowledge base, every parameter of the Standard Model, every measurement of the Hubble constant and the matter density and the spatial curvature and the dark energy equation of state, has been derived from observations made from inside this hole. If the hole is biasing those measurements, the bias is invisible from within the hole. We cannot step outside it to get an uncontaminated view. We are inside the measuring instrument. The analogy is imperfect but useful. Imagine you are trying to measure the ambient temperature of a room, but your thermometer is sitting next to a heat source. The thermometer gives a precise, reproducible reading. It gives the same reading every time you check it. It is not malfunctioning. It is accurately measuring the temperature at its location. But the temperature at its location is not the ambient temperature of the room. It is the temperature at a specific non-representative position, close to a heat source. And if you do not know about the heat source, you will believe the thermometer, and your belief will be precisely wrong. The KBC void is the heat source. Our measurements are the thermometer. And the room, the universe, is warmer on average than the reading we are getting. But here is what I want you to take away from this, and it is something that the popular framing of this story, the "we live in a void" framing, often misses. The KBC void is not bad news for cosmology. It is not evidence that the science is broken, or that the measurements are meaningless, or that the universe is unknowable. It is the opposite. It is evidence that cosmology is mature enough, precise enough, and self-aware enough to identify its own systematic biases. The fact that we can identify the KBC void at all, that we can measure the galaxy number counts at different redshifts, compare them to theoretical expectations, identify the discrepancy, and characterize the underdensity responsible, is a triumph of observational cosmology. The fact that we can then ask, how does this underdensity affect our measurement of the Hubble constant? and answer that question with quantitative predictions that can be tested against independent data is a triumph of theoretical cosmology. The fact that we are actively planning and executing the surveys that will definitively test those predictions is a triumph of the scientific method. We are not helpless inside the whole. We are mapping it. We are characterizing its properties with increasing precision. We are calculating its effects on our measurements and designing the observations needed to separate those effects from the signals we are trying to measure. We are doing, in short, exactly what science does when it discovers a systematic bias, acknowledging it, quantifying it, and correcting for it. The Hubble tension is the most visible consequence of the KBC void's potential influence. For years, it sat in the data as a stubborn 5 sigma discrepancy that resisted every proposed resolution. New physics was invoked, dark energy models were modified, early universe physics was examined and re-examined. The possibility that the answer might be, in part, topographic, that we simply measure the local expansion rate from a non-average location, was acknowledged in the theoretical literature, but not widely adopted as the primary explanation. That is changing. As the evidence for the KBC void from multiple independent surveys grows more consistent, as the theoretical framework for its dynamical effects on local measurements becomes more precise, and as the observational tests of the void hypothesis accumulate and begin to converge, the geographical explanation for part of the Hubble tension is gaining credibility. It is not the complete explanation, but it may be the most physically motivated, most observationally grounded component of the eventual solution, the part that required no new physics, no new particles, no modifications to general relativity, just a more honest accounting of where we are. There is a broader lesson here that extends beyond cosmology. It concerns the relationship between the observer and the observed, the impossibility of fully separating where you are from what you see. Every measurement is made from somewhere. Every sample is drawn from a specific population. Every science is done by observers who are embedded in the system they are studying, who cannot step outside it, and who must therefore account for the specific properties of their position within it. Physics has grappled with this truth in various forms. The Heisenberg uncertainty principle is, in part, an expression of the fact that measuring a quantum system disturbs it. General relativity is, in part, an acknowledgement that there is no preferred reference frame from which to make absolute measurements. Every observer is embedded in a curved space-time and must account for that embedding. The cosmological measurement bias from the KBC void is another instance of the same principle operating at the largest observable scales. The observer is inside the thing being measured. The measurement is therefore local, specific, and non-representative, unless the difference between the local and the global is explicitly accounted for. There is an interesting parallel here with the history of geology. For most of recorded history, humans assumed that the ground beneath their feet was stable, old, and essentially permanent. The surface they stood on was the reference point. It was not an observation platform at a specific, evolving position in a dynamic system. It was just the Earth. The discovery of plate tectonics in the 20th century revealed that this assumption was wrong. The ground itself is in motion, riding on plates that have been drifting, colliding, and subducting for billions of years. The The stable ground assumption had been producing subtly wrong inferences about earthquake distributions, mountain formation, and the ages of geological features, all of which made more sense once the dynamic reality of the ground itself was understood. The KBC void is cosmology's version of plate tectonics. The ground we stand on, our location in the cosmic web, is not the neutral, fixed reference we assumed. It is a specific position in a dynamic, structured universe, and that position has been systematically biasing our measurements in ways we did not account for because we did not know the ground was moving under us. Now that we do, or are beginning to, the science can proceed with more honest foundations. We built telescopes to see beyond our immediate surroundings. We built the cosmic microwave background experiments to see all the way back to the beginning of time. We built the galaxy surveys that revealed the KBC void's existence. We built the James Webb Space Telescope, whose supernova observations will eventually help determine the void's precise contribution to the Hubble tension. We are building the Vera Rubin Observatory, whose galaxy census will map the void's profile with statistical precision we currently lack. We are compiling the cosmic flow's peculiar velocity catalogs that trace the gravitational dynamics of the void's environment in real observational data. All of this is the ongoing effort to see more clearly, to reduce the distortion introduced by our specific, local, non-representative vantage point in the cosmic web. The fact that this effort is succeeding, that we can now identify our own observational biases, quantify their magnitude, and design the observations needed to correct them, is a measure of how far the science has come. 100 years ago, we did not know other galaxies existed. 50 years ago, we did not know the universe was accelerating. 20 years ago, we did not know the local galaxy density was systematically below the cosmic average. Today, we are beginning to understand how that below-average density has been influencing every cosmological measurement made from this location, and how to account for it. We are inside a cosmic hole. It is approximately 2 billion light-years across. It is 20 to 30% emptier than the cosmic average. It is making our measurement of the universe's expansion rate systematically higher than the true global value. And it may have been making that measurement systematically higher for as long as we have been measuring, without anyone knowing. Consider the specific human timeline of that non-knowing. Edwin Hubble measured the expansion of the universe in 1929 from inside the KBC void. Every subsequent generation of astronomers, every team that refined the Hubble constant, every survey that measured the large-scale structure, every CMB experiment that inferred cosmological parameters, worked from inside the void, without knowing they were inside it. The Hubble Space Telescope was built, launched, and operated for decades inside the void. The discovery of dark energy in 1998, made from Type 1a supernovae at distances spanning the void and just beyond, was made from inside the void. The precise CMB measurements of Planck, whose inferred Hubble constant now sits 5 sigma below the local measurement, represent the first cosmological dataset that genuinely probes the global universe rather than the void interior. In that sense, the Hubble tension is not just a discrepancy between two measurements. It is the first time we have simultaneously had a precise measurement from inside the void and a precise measurement from outside it, and noticed that they disagree. The disagreement is the void announcing itself. The void that has been shaping our cosmology since 1929, from the inside, finally visible because we have built instruments sensitive enough to see it. Now we know, or at least we are beginning to know. The surveys are running, the simulations are constraining the possibilities, the supernova data is accumulating, the peculiar velocity catalogs are growing, the weak lensing maps are being built. The answer is coming. And when it arrives, when the contribution of the KBC void to the Hubble tension is measured precisely enough to either resolve the discrepancy or firmly establish that something more is needed, it will not just be a measurement of an underdensity. It will be a measurement of ourselves. A cartographic milestone in the long project of figuring out exactly where in the universe we are. Not just where our galaxy sits in the cosmic web, but how that position colors every observation we make. How the specific accident of our location, inside a void, on the edge of another void, in a galaxy group at the outskirts of a supercluster, in a local universe that is systematically less dense than the average, has shaped every number we have ever written down about the cosmos we inhabit. The universe is very large. Our position within it is very specific. And for the first time, we are beginning to account for both of those facts simultaneously. That is not a crisis. It is progress. And the progress has a specific, beautiful quality that is worth naming directly. The KBC void was found not by building a new telescope with a new capability, but by asking a new question of existing data. Ryan Keenan, Amy Barger, and Lennox Cowie did not discover the KBC void because they had better instruments than anyone before them. They discovered it because they asked carefully and systematically whether the galaxy counts in the nearby universe matched the galaxy counts at larger distances. They compared what they saw to what the theory predicted. They found a discrepancy, they published it, and they changed permanently how cosmologists think about the relationship between local measurements and global parameters. The tools of discovery are not always mirrors and detectors and cryogenic electronics. Sometimes they are analysis frameworks and careful statistics and the willingness to ask whether the ground you stand on is really as ordinary as you assumed. The KBC void was hiding in plain sight for decades. In the galaxy surveys, in the number counts, in the pattern of the nearby large-scale structure. It was always there, in the data, waiting for someone to look at it the right way. Now we see it, now we know where we are, a little less certain than we were, a little more honest, standing in a hole 2 billion light-years wide, looking outward through our instruments, and beginning to account for what it means. That is not a crisis. It is progress.